Microphones are muted, so please do submit your questions via the question and answer window in Zoom, and we will answer as many questions as possible live. Feel free to subscribe to our Seminar series and sign up for our newsletter at the links shown on the slides. Thieme is a medical and scientific publisher based in Germany. Our portfolio includes the chemistry.
In part of this event, I'm really grateful to Thieme and to Synthesis in particular for organizing it. So we have 4 speakers today, 3 from academia and 1 from industry. And the point of this event really is to showcase some of the most recent and exciting chemistry happening here in Germany. So without further delay, I'm going to start introducing the first speaker. That is John Molloy from the Max Planck Institute of Colloids and Interfaces. So John did his PhD at the University of Strathclyde in Glasgow in the UK with Alan Watson, and then came to Germany as a Humboldt Fellow working for Ryan Gilmore. And then he started his independent career at the Max Planck. And he has had a very successful career. Brady was awarded the ERC starting grant. And he's doing some of the most exciting chemistry dealing with boron species. So without further delays, John, the stage is yours. It would be great if you could share the talk. Thank you.
Oh, what's going on here? Yep, should be okay now. 2 seconds. Yep.
Still on, John, and I'll confirm that we can see the screen. Yes.
Yep. Thanks very much for the kind introduction, Daniele, and thanks to Thieme for inviting me for this talk today. It's really exciting to share some of the chemistry that we've done over the past few years. So you'll be able to tell already by the title, but we're mainly an organoboron research group. And where there's many reasons that you should study organoboron chemistry, the real reason that attracts us is due to its use in organic synthesis. And what I mean by this is that you can easily interconvert organoboron molecules into almost any other functionality. And when you consider that you can actually do this in a stereospecific manner, this allows users to explore chemical space in a controlled manner to generate next generation therapeutics, for example. Now, on the note of therapeutics, it might not be the first thing that sort of comes to your mind, but boron's becoming increasingly popular as a sort of molecular antenna in drug discovery. Due to its various binding modes, there has been an influx, a recent push towards drug discovery in this area, highlighting bortezomib, which recently gained blockbuster status, and these heterocycle chemotypes that have been developed by Dennis Hall and co-workers. Now, central to how we understand how boron works as a reagent and both in drug discovery is boron hybridization. So in this case, boron in its trigonal planar form is electrophilic. In its tetrahedral form, it is then nucleophilic. And it's actually this difference in reactivity that really attracted our research group. And we sort of posed the question, how can boron hybridization be used in the excited state using photoactivation? Now, I wouldn't say that this is an understudied section of photocatalysis, but I would say it's often oversimplified, where we take boron molecules, we turn them into boronates, and we use this to generate carbon-centered radicals. Now, when you consider that I've just mentioned all the desirable properties about retaining the boron and having a complex molecule, what we believed would be a more desirable construct would be if we could take simple organoboron precursors and efficiently change these into complex organoboron scaffolds in a single or a couple of steps. Now, central to this, we wanted to see how boron hybridization could particularly influence photoactivation and also the intrinsic reactivity that comes afterwards. So being nucleophilic or electrophilic, how does this influence reactivity? And the 2 high energy intermediates that we've looked at are alpha bororadicals in the T1 excited state. For the interest of time today, I'll focus predominantly only on alpha bororadical chemistry. Now, the big question is, why should we focus on alpha bororadicals? And the reason for this is we've seen this as a prime opportunity to take a high energy intermediate and develop these sp3 organoboron molecules. And more importantly, hybridization has also been shown to already affect reactivity with regards to alpha bororadicals. And as you can see here, typically electron deficient alpha bororadicals can engage with electron rich somophiles. And more recently with Zard and co-workers, they've shown that electron rich molecules can engage electron poor somophiles. So in this case, hybridization had already been shown to have an effect. Now, we're definitely not the first group to think about generating alpha bororadicals. There's some fantastic work with radical initiators, initially by Beatty, Zard, Renault and co-workers. Also, we're not the first with photoactivation as well. So typically you generate a radical and you can add this to a vinyl boron species. And again, this has been done with great effect by Agarwal and co-workers, Studer, Shi, Masawa, and many, many others. Now, where we sort of came in, we've seen a sort of niche section here, where these alpha haloboronic esters, which can be easily accessed by Matheson homologation. We were interested that these had only been activated either by using powerful photoredox catalysts or palladium insertion and light combined together. Now here we actually took inspiration from alpha carbonyl systems, where there have been a lot more reactivity shown that you can achieve direct excitation to allow homolytic bond cleavage, or activation via electron donor acceptor molecules to generate alpha carbonyl radicals. Now, in this case, the hypothesis is quite simple. Can the p orbital hybridization state replicate a pi star and essentially weaken this carbon-halogen bond and give us a direct method for accessing alpha bororadicals so that we could subsequently use these in downstream reactivity? Now, I had a very fantastic first PhD student, Alessandro Marotta, who worked on this project. And we started with the weakest bond, the carbon iodide. And unfortunately, when we exposed this to 317 nanometer light, we got complete recovery of start material. However, when we introduced 2,6-lutidine as an additive, you can see here by using two 427 nanometer lights, we could achieve good reactivity and good selectivity, in this case for the E isomer. Now, one key thing that I want to highlight here, that this was really selective for 2,6-lutidine. So when we remove the functionality and we kill reactivity, and other Lewis basic additives were not effective for this reaction. Now, Alessandro obtained a fantastic scope on this effort, on this project. And you can see here a few of the ones that I actually want to highlight. Here, you can see that when we remove the methyl group, what we actually require is to increase the steric bulk of this Lewis base to 2,6-diterbutyl pyridine. But we could engage a range of different styrene and good selectivity and reasonably good yield as well, using only light and a Lewis basic additive. Now, our control reactions and our mechanistic probes, initially, by looking at boron hybridization, you can see here, as soon as we form that boronate, we kill reactivity. When we change to the bromide and chloride, we also inhibit reactivity, but you can simply restore this by adding sodium iodide, which does an in situ Finkelstein. And of course, with no light, we have no reactivity, and with no 2,6-lutidine, we have no reactivity too. Now, probing the presence of a radical and radical chain process, we carried out your standard radical clock reactions that proved well supported, that we generate a benzylic radical, and also that we generate this alpha boro radical. And quite interestingly, we see pure selectivity for the alpha boro species, even in the presence of an excess of other metalloids. And just to clarify that there's no chain process, we get a quantum yield, which shows that this needs continuous irradiation for reactivity. Now, I mentioned that the boron p orbital, we wanted to see if this affects reactivity, and looking at the ground state structural analysis, we can see that we really have an overlap between this boron p orbital and the sigma star of the carbon iodide bond, which we propose essentially weakens this carbon iodide bond and lowers the LUMO, similar to the carbonyl system. Now, I'm going to change topic a little bit here and move towards these multifunctional C1 units that have been shown to undergo closed shell reactivity fantastically by Cho, Schoenebeck, Gevorgyan and co-workers. And where we became interested here was, again, could we achieve this activation to generate an alpha bimetalloid radical? And essentially what this would give us is then a radical that would form a molecule with two synthetic handles. We would be able to explore 3D chemical space subsequently via chemoselective activation of these competing bimetalloids. So boron-boron, boron-silicon, and also boron germanium. And again, we weren't the first people that have sort of been able to access these radicals. Again, I just want to highlight some work by Gevorgian and Schoenebeck, where they show that, again, you can use palladium and light to generate these alpha bimetalloid radicals. And we hope that we could complement this by using our lutein system. So again, a long story short, what we have to use in this case is our 390 nanometer light. So we have to go to shorter wavelengths in this case. And actually what we've seen was that these alpha bimetalloids gave us a more electrophilic radical, which means we could engage a wider range of these electron-rich somophiles in this case. So of course we could engage styrenes to get us through to these allylic bimetalloid systems. We could also engage siloenol ethers to get through to these beta boroketones. We could engage dienes to get through to these systems here. And by a cascade reaction, we could form these small ox-indole fragments as shown here. Now, a few key points that I actually want to highlight here is that this tertiary amine might be a bit troublesome if you're going to be using photoredox catalysis due to oxidation. And we could also incorporate aryl bromides and aryl iodides in this system, not shown here, which could cause complications with the palladium systems that I've identified in the past before. Now, here we had a rough idea of what was going on, and what we believed was happening is that we were generating this charge transfer complex where the nitrogen lone pair was donating into the sigma star of the iodide and essentially shifting this to a wavelength that can absorb the incident light and enable activation to generate the alpha boron radical. Now, when we look at our first system, you can see here that we have a clear new band when we add the lutein to the system. But like all things chemistry, it's not always sunshine and rainbows. When we moved to the other system, so looking at our alpha bimetalloid, we really couldn't identify any clear EDA complex that occurred at the incident light of around about 390. There were some tails, but nothing so clear-cut to support reactivity. And again, we tried a lot of different processes, and I've wrote here that it's unsuccessful, but I would say it was more not reproducible. We sometimes seen solvent effects, or sometimes we've seen concentration effects, but nothing clear cut where we could really say, okay, this is definitely an electron donor acceptor complex. But the reality is that if you put this molecule in on its own, it doesn't photoactivate. When you put this in with 2,6-lutein and you shine a light on this, this is when you get activation, as shown here by the generation of triiodide over time. Now, at this point, we were really scratching our heads, and we turned to our collaborator, Ignacio from University La Rioja, and we looked at a theoretical investigation of both the role of lutein and the role of the boron p orbital. Now, here we were looking to probe this charge transfer complex. And Ignacio could identify that we can form this with a bond length of 3.16 angstroms and an energy of formation of 6 kcal per mole, suggesting that it exists in low concentration in solution. Now, in this case, the calculated absorption, when you take in concentration effects, comes around about the incident light, right, of 390 nanometers. And again, computation identified that in the excited triplet state, rather than a single electron transfer from lutein, what we actually see is this barrierless homolytic bond scission, which generates an alpha boron radical and generates this iodine radical, which is stabilized by lutein via a 2-center free electron complex, as supported here by Nicturo and Breslow and Barriault more recently. We could not detect any boron hybridization via activation in this role. So what's the role of the boron p orbital? Well, it lowers the radical it raises the radical stabilization energy, generating a more stabilized radical. We also show that again, that we have this lowering of the bond dissociation energy in the presence of boron. And we also have efficient overlap with the d orbitals of silicon and germanium that lower, again, the LUMO, weakening this bond. Now, what's happening in this reaction then? What we propose is that we are generating this charge transfer complex that aids excitation of our alpha iodide species. And not like conventional EDA chemistry, what we propose is that we get a homolytic bond scission. We generate an alpha boral radical that can then engage a somophile. And in this case, the iodine radical can partake in H-atom abstraction or recombination and elimination or oxidation and deprotonation, depending on what somophile you use. Now, probing the triplet excited state, I mentioned previously that we wanted to essentially have a mild system where we could sort of introduce catalysts to influence reactivity that comes afterwards. And here we could introduce an iridium photocatalyst that could enable direct access to the Z isomer, giving us a stereodivergent approach to these allylic boronic esters. Interestingly here, this actually points towards an energy transfer process, which is also supported by Rovis and co-workers in their chemical science. So it looks like basically we have energy transfer catalyst activation of this alpha iodide component. Now, shortly in closing, I mentioned that we wanted to make molecules that can actually be useful in organic synthesis. We could show that you could achieve chemoselective activation via the Sakurai activation to make the vinyl boron species in syn diastereoselectivity. We could do your standard boron allylation to generate the vinyl silicon. And in this case, the divergent approach to the Z isomer allowed us again to get complementary diastereoselectivity for the allylation to give syn here with the vinyl boron. And lastly, we could do a range of different transformation on these geminal boron system to generate small borylated, small fragments for drug discovery. Sorry. Now, in closing, I hope I've shown you today how some of the first studies in our group allowed us to generate alpha boral radicals and alpha bimetalloid radicals supported by electron donor acceptor chemistry, and that we could use these for efficient electron donor for vectors to explore chemical space. In closing, I've highlighted some of the fantastic work that's been done here by our co-authors in bold, and I'd just like to thank all of our funding bodies that have really supported our science, and of course, once again, for Daniele and Thieme for the invitation for this talk.
Great. Thanks, John. That was a really good talk. So I think, okay, questions are starting to come up. People are also saying very nice talk, which is true. So one question is why the carbon iodine bond? Okay, a couple of questions like why carbon bond? So have you tried alkenes instead of alkene in your chemistry, John?
So alkynes instead of alkenes?
Yes.
We didn't try this, but there's a fantastic paper that came out recently in ACS catalysis by Honggeng Wang. And he showed that essentially by using similar activation, I think he uses a manganese catalyst as well, he can do alpha halogen atom abstraction, and these alpha boral radicals add to alkynes and then do halogen atom abstraction. So he makes the vinyl iodides. We didn't try any alkynes in our system. We tried some aliphatic alkenes, but it seems like the alpha boral radical is really not electrophilic enough, or it might be that this is energetically uphill, that we might need to put a bit of temperature into this, because we're going from a stabilized alpha boral radical to this secondary alkane alkyl radical could be the problem behind this.
So another question from Juntao Ye, that is an expert of boron radical chemistry and everything, which is something that I was thinking as well. Why is the Lewis base not coordinating the boron? Shouldn't that be the best Lewis acid in the system, especially if you have the stereoelectronic effect?
No, it's a great question. It's something that had me pulling my hair out for a good while as well, because it's something that comes naturally, right? You think that the Lewis base should go directly to the boron p orbital. I think that's what happens when you take away these two methyl groups. So when the two methyl groups of lutein are really important, and I think that it inhibits that donation into the boron p orbital. And the reason why I think that is when we change the pyridine or we change the DMAP, we shut down reactivity. We have NMR evidence at that point that you actually see exchange at boron, so quite similar to chemistry that's been developed by Steve Lay and co-workers. However, when we have the lutein, both experimentally by NMR, we don't see any coordination to the boron p orbital. And also, theoretically, Ignacio's also looked at this in great detail when we don't see any feasible coordination between the nitrogen or lutein and the boron p orbital.
And another question is, have you tried to form a tertiary alpha boron radical in your chemistry?
Yeah, so we did that. We've done this in Alessandro's project, so we didn't do this in the alpha bimetalloid chemistry, we've done it in the alkyl system. And what I will say is that we could generate it efficiently, but it was actually not the best radical for engagement with the somaphile. So the reaction that we actually had, if we do this at room temperature, we see no reactivity. If we heat the photoreaction, you then see around about 50%. So we've looked at the tertiary systems as well, but only with alkyls. We've not looked at it in the bimetalloid system because these are a bit harder to synthesize.
Okay. There's now a question from Joshua, which is asking, one second, yeah, I think you answered partially. His question is about the 2,6-lutidine and if other pyridines can actually form media complexes with the alpha boron iodide, and he would expect to have a greater steric effects from the substituted pyridines than the unsubstituted.
Yeah, it's mostly a steric problem, and like I said, we can see this in EDA for the first system. For the second system, we don't see it by EDA. What we are currently working on at the moment, there's a fantastic physicist at Leipzig University that focuses on photothermal analysis, so infrared. We're actually looking to develop systems where you can, well, a small system where you can measure electron donor acceptor complexes and actually point towards where in the molecule it's binding based on stretching of the bond. So hopefully that can reveal a bit more in the future.
Maybe the two quick questions and quick answers, please, because we need to move on. One is, have you tried the BE pin instead of the standard B pin with the ethyl groups instead of the methyl groups? Because these are much sterically linked, and they wanted to know if you see a stop in reactivity.
That's a good question. So whenever we've tried anything different with the boron, as long as the boron p orbital's there, it still activates. I don't think we tried directly the FOB pin, but I think we showed the benzophenol derivative, so essentially with 4 phenols. I don't think we included it in the manuscript, but we showed that essentially that didn't affect sterics as well. But again, it looks like sterics on the boron doesn't really play much of a major role when you're actually having this N to sigma hole interaction between the nitrogen and the iodide. The only way that you stop reactivity is actually by occupying that boron p orbital, which messes up with the electronics of the system and makes the carbon iodide bond less weak in this case.
Okay, the last question, which might be a little bit difficult to answer in a short amount of time, asks you about which are the key properties of boron and silicon in terms of catalysis and synthesis. So to make it very short, what do you think is best, boron or silicon?
Yeah, well, I'm obviously in near Berlin, where Martin Oostreich does some fantastic silicon chemistry, right? So I don't think I'd say anything bad about silicon. I think they complement each other a lot. Obviously, I'm a bit biased, where I would say that I think that maybe boron's a bit more powerful with the different transformations that you can do. But when you can include both together, like the bimetalloid system, I think this becomes really powerful. Essentially, especially when you consider that both of them have different reactivities and different activation modes. So fluoride activation with silicon, of course, you can't do this with boron, whereas the boron p orbital plays a major role in the reactivity of boron molecules. But yeah, I mean, you could write a book on that question, right?
Of course, yes. Okay, with this, John, thank you very much for your great talk. And yeah, congratulations again for your results, and all the best for the future. And with this, I'm going to share my screen and I introduce the next speaker. Okay. 1 second. Okay. So hopefully you can see my slides. So the next speaker is Dr. Martin Klein, and he's the industrial speaker of the sessions from Merck in Darmstadt. So Martin did his PhD at the University of Mainz, working for Van Vogel, so in electrochemical development. And then he joined immediately Merck Electronics, where he's now a lab head in chemical process and development. And I'm very excited about this lecture that is going to tell us how to integrate electrochemistry into chemical process development. So Martin, the stage is yours. You are free to share your slides.
Eva, thank you for the nice introduction. Hi, everyone. Okay, the chance to be here. As you've seen on the last slide a little bit, I was working on very specific and pharmaceutical relevant molecules and the preparation of them via electroorganic synthesis in mines once again. And then now I'm here in the process development, still working on electrochemistry or electroorganic synthesis in that case, but focusing a little bit less on the complexity of new molecules, but more on the technical application and the full scalability of this. I would say it's a very cool and kind of renewed renaissance technique for chemical synthesis. As most of you heard the term of electroorganic synthesis, I guess, in the last recent 5 to 10 years, very often in many publications, electroorganic synthesis became a renaissance because it's a new tech, or it's a technique which has a chance to prevent wastes coming from reaction, as using electrons as a kind of traceless reagent to drive reactions. Besides this, the electroorganic synthesis also ensures that the reaction can be driven very safe, as reactive intermediates are often just produced in situ in reaction solution. And if you turn off the current, you also turn off the reaction, and everything stops from being highly exotherm. And the third big advantage of this technique is the radical-based chemistry. It offers you often a very unique reactivity compared to classic thermochemical synthesis. In all of this interest of electroorganic synthesis, Merck became interested in the application for process development, and therefore we came into the ETHOS cluster. ETHOS is a future cluster founded from the German Ministry of Research and Education. And within this cluster, several academic partners as well as industrial partners working collaboratively on different projects for integrating electrochemistry into their facilities. And one project we are working on, or I specifically working on, was with the MPE for chemical energy conversion at Mülheim at the Ruhr. And I want to present you today the results we got in a collaboration with the MPI. Just to bring you all on the same point, I will just get a little bit on the terminology, because I think electrochemistry is not something which is all familiar to most of the organic synthesis community. So within an electrochemical reaction, we are just applying an electric current into an electrolyte. With this, an electrical field is set up to between two electrodes, and if the energy of the field is high enough to drive the electron transfer between a substrate at the surface, then a chemical reaction occurs. And in every classical chemical redox reaction, both an oxidation and a reduction will always occur simultaneously. At the anode, the oxidation takes place, where we have the electron depletion, and at the cathode, we have an electron excess, where the reduction takes place. Both reactions can be separated with a separator to and separate them in two different spaces, so that there's no competitive reaction. If you want to drive the performance of electrochemical reaction, you can choose between the classical conventional chemical parameter space, like solvent, temperature, and so on, but you can also add the electrolysis parameters like electrode material, current density, charge, to enhance the process selectivity. And the very typical kind of chemistry we were looking on the last year was a hydrogenation reaction. Hydrogenation, especially in that case, hydrogenation on a catalytic way, is a well-known reaction in most organic synthesis labs. And something is very easy to perform, especially on lab scale, because usually you just dissolve your material in a flask, you add a hydrogen balloon and a few milligrams of catalyst, you stir it overnight or just for a few hours, and then in most of the cases you have a very selective reaction performing your hydrogenated product. But unfortunately, hydrogenation reactions, even though those are very simple and can be scaled, by the way, are not really good for scale, because you have to store the hydrogen, you have to store it under pressure, the hydrogen needs to be transported into the facility. Those reactions usually requires high pressure and high reaction conditions, because running a reaction over 24 hours in like a 1,000 liter or 4,000 liter reactor is a very long reaction time. And from terms of sustainability, the hydrogen which is often used in that case is gray hydrogen, means it's generated from reforming of natural gas, and then explaining 9 tons of CO2 per ton of hydrogen, which decreases the overall sustainability of the reaction. But diving deep into this, we've been working on the design of an electrochemical reaction to transform, in that case, the hydrogenation of nitriles into the relevant and the corresponding primary amines. We've been starting this reaction using benzyl cyanide as starting material, and then do the reaction to bring beta-phenylethylamines as a very kind of relevant structure motif in most pharmaceutical compounds. We started this reaction with an H-type screening system, which you can see over here. We used a nickel foam as a catalytic active metal cathode, and a DSA, which is a dimensionally stable anode, to enhance the anodic reaction. The cathode reaction is when the hydrogenation of the nitrile were combined with the anode reaction as oxidation of water into oxygen. It's a harmless byproduct in that case. We did initial screening, and with combined and optimization, we found that the use of a nickel foam with DSA electrode at 50 milliamps per square centimeter was giving a very high yield into the hydrogenated product. When switching from the nickel foam cathode into a nickel plate, the yield dropped significantly, but still having a very high selectivity. So there's just no conversion in that case, mainly because if you have a small surface on the electrode, there was mainly hydrogen formation as a side reaction. When performing the same reaction in an undivided cell, where both electrodes are attached to the same electrolyte, we saw just 31% yield. In that case, it was mainly because there was the oxidation of the primary amine of the product at the surface. With the test reaction, we performed the same, or we performed the technique. We used the same system under a hydrogen atmosphere, and we saw only very low reactivity. Why is that? We did some mechanistical studies, and via CV we can confirm that there was no direct reduction of the substrate, as the reduction of the substrate happens in the same way where the solvent reduction takes place at minus 1.5 volts versus silver chloride. And adding sulfuric acid, we've seen the hydrogen absorption on the nickel surface, and in presence of the substrate, there's a slight shift towards a more negative potential, which then comes from the reaction of the absorbed hydrogen. We think that the formation of this nickel hydride species is in then also the active form which promotes the hydrogenation, and the absorption itself onto the nickel surface is then promoted by electrochemistry instead of just absorption with hydrogen. And that's the case why we think that there is way better reactivity with the nickel plate towards the system instead of using nickel and then hydrogen on top. We did some SEM pictures of the nickel surface to see why the nickel foam has this very high reactivity. And what we observed is that the sulfuric acid is partially corroding the nickel in the first place of the reaction, But in terms of the electrolysis, the nickel itself got replated on the foam, forming these very nice microclusters, which enhances the surface reactivity as well as giving high conductivity of the nickel itself. In the end, we also observed no high loadings except for just a few ppms of nickel in the product dissolved in the solution. With these developed reaction conditions, our collaborators at the MPI did a very nice scope, testing that different aliphatic nitriles as well as aromatic nitriles can be converted in that case, still using the screening cell. We figured out that mostly the bulky substrates are converted less successful than a little less bulky substrate, which is mainly because there's a heterogeneous reaction and the migration of starting material into the cathode is in that case the limiting step. So, and with this in hand, we then started to think about how we can make this a process. One of the big issues is the scalability of those screening systems. We have an electrode distance in that case of 2 centimeters, which is very large. And if you think of scaling a process where you have a heterogeneous surface, if you double the volume, if you double the area of the electrode, you will have 8 times the volume because you have the cubic to square problem in that case. So what we made then is we transformed the electrochemical reaction from a screening type batch cell into a flow cell, where the electrode distance is very close then, with a higher surface to volume ratio for the inner electrolyte, which then significantly decrease the overall cell voltage, leading to better energy efficiency in the overall system. Those type of sandwich-like flow cells can be inherently scaled by especially numbering up systems, which means you have multiple cells just cut in a cascade or running parallel to increase then the batch amount you're running through. The overall cell looks like this, where we have here the DSA anode separated by a Nafion membrane. DSA as well Nafion are well known from chloralkali electrolysis process and therefore lightly commercially available. And on the cathode half, we have a nickel foam where the electrolytes flow through this foam and coming out in a reduced way. The foam in that case also works as a turbulence promoter for the system. We brought the system to a full electrolyzer setup where we have a cathodic chamber and an anodic chamber. We pumped the system through the cell in a recirculating way so that we can enhance the mixing efficiency in the system, as well as the option for continuous probing of the system in the electrolyte. With those type of flow cells, we have an effective heat exchange to maintain a constant temperature also. We scaled then the reaction from the small flow cell into a larger flow cell, still on, let's say, kind of lab scale, using 50 milliamps per square centimeter, which is in terms of electroorganic reactions already a very fast reaction. We still have 90% yields, and we're able to produce the compound in the system with 20 gram scale, using a precipitation of the hydrochloric salt as an isolation strategy. And with this, we were able to obtain a pure product without any notable amount of nickel or any other impurities inside, in a very simple conversion way in that case. The foam itself is stable over time, so we were able to run the electrolysis with the same system, with just flushing solvent after every reaction through the system to clean it a little bit, but no complete cleaning over time. And after 12 electrolysis, we still had a stable performance of the foam. Yeah, so to close everything, I want to explain that we designed a new reaction which is sustainable and scalable in terms of the conversion of nitriles under very mild conditions into the corresponding primary amine. The setup itself is very cost effective because we're using a 2-electrode system with constant current application. This is inherently scalable in that case. And the big benefit of nickel foam compared to other electrochemical hydrogenation techniques is that it's largely commercially available. And the system, which was then presented still on lab scale, had already high productivity as we had conversion of 4.2 kilogram per day and square meter of the phenylethylamine for the benzylamine into phenylethylamine. With this, I want to close everything. I have to say very much thank you to our partners at the MPI. A very special thank goes to Rock Nahobe and Marcel Perner, still in the group of Sigi Waldvogel, which did a lot of or most of the synthetic work in that case, did all the optimization.
Cool. Thanks, Martin. That was really interesting. Maybe while people start to ask questions in the chat, I'll ask you a couple that I was really interested in. So when you discussed how your reactor looks like, you showed that you can put something to separate the anode and the cathode, correct? Right? Yeah. Yes. So how do you choose the membrane? Which are the options available?
So the membrane chosen was in that case Nafion for its proton exchange membrane. So this is a perfluorinated material containing sulfonic acid groups on top. And as we were using a system under acidic conditions, we are starting everything with a proton ion exchange membrane in that case. Alternatives are also just a semi-permeable membrane, just more like a polyethylene or polypropylene film, which is non-ion selective, but stops the passive diffusion a little bit, or an anion exchange membrane.
Okay. And listen, when I look at the transformation that you showed, if I would want to run it in an academic lab, I would just tell a student just use an hydride source to reduce a nitrile into primary amine. So are hydride sources like a no-go for you guys in industry?
I would not call it a no-go, because if you want to do it, you can. But if you think about a hydride source, you have to store it. And if we're running on production scale, we're talking about a few 100 kilograms sometimes of the starting material, which means then if you have a hydride source, like in 2 or 3 equivalents, then a round of, I don't know, 200, 300 kilograms of a hydride source, which has to be added stepwise into your system. You have to check that there is no hydrogen evolution as a side reaction occurring. The exothermy of the reaction has to be controlled. So it is possible, but you don't really want to do this.
Okay. From the chat now. So how do you go into deciding between nickel plate versus nickel foam? I guess is there a rationale when you design these apparatuses, like which type of metal alloy you're going to be using, or it's just a random screening?
A combinatorial approach. So we thought about higher surface area may lead to a more effective reduction or to a more effective formation of hydrogen. Both were an option, and then we screened both materials in comparison, and then we saw that the foam is much more effective. And
then what about chemoselectivity for other types of functionalities. Yeah, I guess that makes sense. Like, is your method compatible with other groups that you could reduce, like, for example, an imine? Or, I mean, I saw that you can tolerate carbon-hydrogen bonds, which I think is really great. But did you try other functionalities that could be hydrogenated with a system?
Yeah, we tried. And there is a lot of different groups which can be transformed by this way. Very interesting is, for example, for the scope, for the aromatic nitriles, we form, yeah, in that case, benzylamine, and we don't see any C and bond cleavage because there's a likely similarity to other benzyl deprotection methods.
Mm-hmm.
The benzyl is very stable. Nitro compounds can be reduced by that way, as well as double or triple bonds.
Okay. And then there's someone that also asks if you could clarify what ELSC-DSB means that you mentioned in your introduction.
Oh, that's just the official company intern name of the lab I'm head of. EL is for electronics because I'm part of the Merck electronics cluster. SC is for supply chain, and D is for development, and SB is then just numeric.
Okay, cool. Okay. There is another technical question, and then we'll have to close it. Again from Joshua Barham. So, okay. You have, okay, so there is a divided cell. Do you flow the two half cell reactions in the same direction, opposite direction? Does it matter? Do the relative flow rates have to be balanced?
We balance the flow rates in that case because the oxygen generation leads to the formation of protons, and we want this to be done in one scale. Both flow directions are also the same in that case. I think the lab system in that case, where we started everything, is still very small. So to fill up, we run against gravity, means we flow from down to up, and then both always in the same direction, and then separate them into different tanks at the end.
Okay, cool. I think with this, we need to close it. Thank you very much, Martin, for your time. It was really great to see your electrochemistry, especially on such a large scale. Thanks again. Okay, so I'm gonna share my screen again. So I'm gonna move on the third speaker. That is Golo Storch from the Technical University of Munich. So Golo did his PhD at the University of Heidelberg, working for Oliver Trapp. And then he moved to the US, working for Scott Miller at the University of Yale. And then he started his independent career at TU Munich. He's also been extremely successful. He also holds NERC starting grant, and he does some really exciting research in the area of flavin and new types of molecules that can actually behave as super electron donor. With this, I'm going to stop here, and I invite Golo to share his screen.
Yeah, thank you very much, Daniele, for the kind introduction. I hope things work with a screen share.
Yes.
Good. Okay, so let's start. Okay, perfect. So let's start. Yeah, first of all, by thanking the organizers for putting together this great meeting. Thanks for Daniele again for the kind words of introduction. And of course, thanks again for the entire audience for being here today. I know some of you are even from the US, so very, very early in the morning. So that's really great. Good. What I want to do within the next 15 minutes is to give you a glimpse, a couple of ideas of what we do in my laboratory regarding flavin catalysis. And well, to start, I'm an organic chemist, and well, I always try to share in the beginning how I got interested in this and how I choose this as a research topic for my independent group. And it all began basically by looking from an organic chemist's perspective at flavoenzymes. And those are enzymes that have the flavin as a cofactor in the center in the active site, which is here drawn as a ball and stick model. And I was really astonished by the diversity of reactions that these enzymes can mediate. These range from oxidations to reductions to the activity as nucleophilic catalyst, but also in O2 activation and basically, in this case, a Baeyer-Willige type oxidation. And so if you would think about a similar catalyst that would be active in these different areas in the organic laboratory, this would be really great. And this is what basically got our lab started. And we are now active in a couple of areas that use these cofactors here as catalysts, as molecular catalysts in the laboratory. You see, the catalyst itself is relatively simple, and all the chemistry occurs at this tricyclic isoalloxacine core here, which is a pretty simple compound. The remaining sugar unit and the ADP are more or less just there to localize the cofactor in the enzyme. So in my team, we look into this from different perspectives. And just to give a brief introduction, on the right side here, this is the quinoid, so-called oxidized form of the flavin. It's also the form that you can buy, for example, riboflavin in, which is vitamin B2. It's a yellow compound. It's very bench stable. And you can excite it by blue light, and it gets to a very strong oxidant. If you reduce the compound into the hydroquinoid form, that's the blue one, it's a reductant and not an oxidant anymore. And if you excite it with UV light, it gets an even stronger reductant. Now, if you don't do that in inert atmosphere, but you have oxygen presence, then these reduced forms are directly converted into these hydroperoxides in green, and those serve as catalytic or very mild versions, I should say, of MCPBA. So these are oxygenation catalysts. And much like this carbon-oxygen bond here, there is a variety of different covalent adducts that are formed with flavins reversibly, which makes them very potent organocatalysts. And so you see the diversity of activity of these flavins already on this slide. What I try to do today is to give you a couple of glimpses of how we try to use this diversity in the organic laboratory. Now, I want to commence with the oxidized flavin here, the quinoid version in the excited state. And basically start with a project that was headed by Andy here, who recently graduated in my group, who found that flavins, or a designed analog, I should say, of a flavin, which has an ester group here, is a very active compound in forming covalent adducts once excited by visible light. So if you use this compound excited with a blue LED and cycloheptadiene, it forms this bond here. If you now expose the compound again to air, you cleave the bond, you release the flavin compound again. So basically you've reverted that reaction. However, in the presence of a persistent radical such as tempo, you are able to productively obtain these alkoxyamines also concomitantly to release of the flavin. Now, Andy thought a lot about turning this into a productive catalytic reaction, and he found that he can also activate dihydroamino acids by a similar reaction that forms a covalent bond between the beta position of the former dihydroamino acid and the flavin. And he could also achieve now a catalytic conversion of model substrates like this into the corresponding alkoxyamines by a flavin catalyst. And we thought that's quite interesting because what you typically do in modification of dihydroamino acids like this, if you do it in a radical pathway, is to generate a carbon-centered radical, for example, by iridium catalysis here, and then have that radical add to the beta position. But in our case, we do it vice versa. We oxidize or activate the dihydroalanine and then trap it with a different reagent. And so this was possible for a variety of different amides. Some of them are shown here. And I want to point out that what you form is always an acyl-imine type product, which is a very potent electrophile and allows for a variety of different follow-up reactions, for example, by treating it with nucleophiles. Now, the same catalyst that I've shown previously is this one in the middle here. And what I want to say is that very often we modify our flavins quite tremendously. And here, if you go to the left and you cleave it under acidic conditions, you release, as expected, the carboxylic acid form of the catalyst. However, if you treat it under basic conditions in order to saponify this ester, you not only achieve that reaction, but you also perform a ring contraction reaction that basically cleaves out this CO moiety here. And we confirmed this truncated analog also by crystallographic studies here in the solid state. So in order to go further, we needed to fully characterize this completely new chromophore in terms of its activity. We typically do that in my group by various techniques, for example, by cyclic voltammetry, where we achieve that these truncated analogs of the cofactor are weaker oxidants, which makes sense because they are lacking a carbonyl group, but they are also quite stronger triplet sensitizers because they have a significantly higher triplet energy, which is interesting in terms of applications in catalysis. Now, the first difference is when we achieved or when we applied these two catalysts to the same substrate, the cycloheptadiene that I've shown to you previously. And you see already a first difference. The flavin catalyst forms the adduct, as shown previously, while the ring-contracted analog as a higher triplet sensitizer, stronger triplet sensitizer, performs an easy isomerization reaction that leads to an electrocyclization and in a catalytic manner forms this bicyclic product. We also observe that they are stronger hydrogen atom abstractors compared to the parent flavins in a glorious type trifluoromethylthiolation reaction, where you see that flavins have no activity, whereas the ring-contracted analogs are quite potent catalysts. Now, what we often look into in my group is sequential reactions, which means that the high stability of our flavin catalysts makes it possible to engage the same catalyst in several steps iteratively. So the one that I'm showing here is a quite complicated reaction. I don't want to go into it in full detail. I just want to show that it's a reaction that goes from a tropolone substrate in the first sequence to this bicyclic product 3, and that the step from 1 to 2 is a step that benefits from triplet sensitization of this enone here, which leads to an alpha cleavage of this carbon-carbon bond. That's the key step. And you clearly see that a ring-contracted flavin mediates that reaction quite efficiently. Now, because it's still active at this point, you can simply continue the sequence and have now the unsaturated ketone here engage in an acyl radical addition reaction, which is made possible by the hydrogen atom abstraction activity of the ring-contracted flavin, which spawns this acyl radical at this point. And you see the entire sequence from 1 to 5 is possible in a relatively nice yield with these flavins, whereas traditional photocatalysts either lack one of these activities or they are simply not stable enough for the entire reaction in one pot. So what I want to say is that hydrogen atom abstraction is becoming more and more interesting for our group with flavin chemistry. And I have to acknowledge work by Tim Langschwager, who is currently a really brilliant student in my group, who looked into something that we've encountered for a long time in my group, and that is the complete incompatibility of THF with flavins by irradiation under air. In other words, if you have a flavin in THF solvent, it very often turns dark, it very often turns sluggish. And what Tim systematically investigated is the hydrogen atom abstraction activity of excited flavins in the presence of THF, which leads to furan as a side product or byproduct. And this reaction occurs concomitantly to the release of the reduced hydroquinoid species of the flavin. And now this is interesting mechanistically, but of course we were thinking about a potential application of this reactivity. And Tim and I came up with the idea to look into dihydroxynorvalines as an unnatural amino acid that is found in various natural products, where we thought this reactivity could be beneficial for. And the approach we took is basically to use a similar hydrogen atom abstraction chemistry to spawn a radical, a carbon-centered radical from a dioxylane, have that add into dihydro amino acids, and then have the protected diol, which you can release the diol from by a simple acidic workup. And this worked out really perfectly. You can take any type of serine, perform the elimination reaction to the unsaturated dihydroamino acid, and then use flavin catalysis to install the masked diol. And this worked for a couple of amides really well. And more importantly, I would even say, is that the deprotection to release the free dihydroxynorvaline occurred under really mild conditions, even tolerant of functional groups or protecting groups like these Bock protected amide here. Okay, so I want to use the remaining few minutes of my talk to introduce a completely different type of reactivity that Daniele had also mentioned in the introduction, and that is the reductive chemistry with excited flavins. The inspiration for this project came from the enzyme DNA photolysis, which is really well studied in biology. The enzyme mediates the cleavage of these thymine dimers here on the right side back to the thymines, the original thymines on the left side. And this is a really important reaction because these thymine dimers are formed by DNA photodamage. So it's really important to have a repair mechanism operative. Now, the way it works is that the enzyme uses the reduced flavin cofactor in its deprotonated form. So you see there's a deprotonated position N1. This gets excited and now acts as a single electron reductant for this green highlighted carbonyl group. That compound is now converted into the ketyl type radical, which triggers a ring opening and ultimately releases thymine. And the reason we became interested in this is because the redox potential of this thymine dimer is pretty negative. So this is actually a really useful reductant if one could control it in the organic laboratory. Now, the key difficulty, of course, is that these reduced cofactors outside an enzyme environment are really unstable under air. They react with the first molecule of O2 they see and form the hydroperoxide species I mentioned in the introduction. In other words, we thought in order to have a controlled reactivity, we need to have a stabilized reduced flavin in order to study its catalytic activity. And we did that by using a conformational bias approach, which means that making use of the different geometry of the flavins in the two redox states. The oxidized quinoid flavin is a planar molecule, whereas the reduced one is a bent molecule. And we installed functional groups in the N5 and C6 positions, which lead to a stabilized reduced form, but a really destabilized planar oxidized form. And that went perfectly well. So now we have reduced flavins that can be purified by column chromatography. You can crystallize them. You see here the X-ray structure with the bent geometry. And you can also study them, of course, now in catalysis. In catalysis, we used a reaction that was pioneered by David Proctor, which is a reductive 5-exotric cyclization. And we chose that reaction because these barbiturate substrates are structurally similar to the thymine dimer, but they also have a really similar redox potential. And now the reaction works by reduction of this ketone to the ketyl type radical, which then adds into the terminal olefin. And indeed, to cut a long story short, this reaction also worked very well with reductive flavin catalysis, which we could, of course, achieve with having these stabilized reduced flavins. The chemical quantum yield is relatively low, but the positive side is, first of all, it's most likely a catalysis-driven reaction, but also it's possible to use gamma-terpenine as a reductant, which converts the oxidized catalyst back to the reduced form, which, of course, is a really innocent reductant, and the byproduct, the aromatic, is also a really harmless reaction product. And nowadays, we know that also quinoid flavins, so the oxidized forms, can be used as a pre-catalyst as long as they are reduced under the catalysis conditions. Okay, with this, I want to slowly come to the end. I hope I convinced you that flavins are really active in the diverse range of reactivities. And I don't want to close without thanking, of course, my entire group. It's a wonderful bunch of people, really hardworking, creative, make my day every day really nice to come to the lab and talk to them and talk about science. And of course, again, I want to thank all of you for the kind attention and already for your questions, and the organizers, including, of course, Daniele, our chair today, for hosting this meeting. Thank you.
Okay, great. Thanks, Colo. It's really nice. Okay, while we wait for people to ask questions in the chat, maybe I can take advantage and ask a couple. So it's really interesting, your ring contraction leading to, this such an effective catalyst. So in the hat reaction, which one is the active site of the catalyst? Do you know?
That's a very good question. We haven't figured out exactly now yet. I think it might be the oxygen on the very right side. I think if
urea.
Exactly. Let me go there quickly. For example, here, it might be this one here. That's, I think, the most logical one. We know they go into the triplet state very efficiently. and have a very, very long triplet state. That's all we know for now. We're currently engaged in a collaboration with Jürgen Hauer here in Munich to get more information about the exact nature of that excited triplet state. And hopefully then we can follow up on that in more detail.
Because if that is the site doing HAT, do you think you could play with the substituent on the nitrogen and maybe add a chiral for the catalyst as well?
Yeah, that's exactly what we are currently doing here. Yes.
Okay, cool. That's great. Good luck. Okay, so now in the 4-pi electrocyclization, is that also triplet energy? So I think in the 4-pi electrocyclization that you showed in a cascade.
This one here?
No, I think the one. I think it was the one after where you showed the.
Oh, this one here. Yeah, this one here, I think is most likely a direct excitation reaction. So the first step here, you can excite tropolone directly, and it undergoes the step from here to here. It might be accelerated by the ring contracted flavin. This might very well be, but that we couldn't prove, and I'm not so sure about it. So the first step, this is also possible by direct excitation.
Okay. And
but as you can see, sorry to interrupt, as you can see, it's a really sluggish reaction. So if you have no catalyst present, you get a very sluggish yield of 3 and you get a lot of decomposition. So it's hard to say if this first step is already the problem or not.
Okay. How does the ring contraction work?
Very good. So because of the 15 minutes, I cut that out. And so it's very interesting. So the lithium hydroxide spawns the hydroxide nucleophile, which adds into the C4 position here. And if this happens, you can then cleave that carbon-nitrogen bond here to have an open chain intermediate. This decarboxylates, so this CO is basically released as CO2. And then the open chain intermediate closes back in, which forms this carbon-nitrogen bond here. And you basically release a molecule of water in a condensation step.
So
that's also why it's really
Norwich.
Excuse me?
It's almost like another Norwich then.
In part, yeah. And it's also really better working if it's an electron deficient flavin. So if you have the ester here, that of course turns that position here more electrophilic, and therefore the hydroxide attack is even better.
Okay. Maybe a last question, so then we can move to the next speaker. Have you tried the ester of the new catalyst? So I guess on the ring contracted catalyst, have you made the ester and checked its properties?
Yes, we have. Actually, maybe I've been through that. So we've of course you first obtain this compound, but in order to have an apple-to-apple comparison, we always use the ester for all of our comparison studies. So of course, then afterwards we had to re-esterify because only then can we have an apple-to-apple comparison. So yes.
Cool. Well, thanks a lot, Golo. It's great to see things going so well. Good luck for the future. Thanks again.
Thank you.
Okay. So now I share my screen again. We go to the last speaker of this webinar. It's Ala Bunescu, University of Bonn. So Ala did a PhD in EPFL, working for Zhu. And then he did 2 postdocs, one at Berkeley, working from John Artwick, sorry for the typo, Ala. And then the other one at the University of Cambridge, working for McGowan. And then he joined the University of Bonn, where she has started a really nice program looking at iron catalysis. She's also been very successful. She has an ERC starting grant and a lot of very interesting paper in this area. With this, I'm going to pass it to Ala and ask you now to share your screen. So you are still muted, Ala? Yeah.
Okay, that's. Oh. Do you see my screen? Okay.
Yes, but we see, yeah.
Okay, perfect. Slideshow. Okay. Thank you very much for a nice introduction. And of course, thank you for the invitation to be part of this seminar session. So today I would like to talk about a project related to CH correlation. But before that, I would like to make just a quick overview of the research in my group here at Bonn. So we are working on two research lines. One is on iron photocatalyzed radical cross-coupling. And in this project, we are trying to leverage intramolecular electron transfer to transform available starting materials such as carboxylic acid and value-added product. And the second line of the research, which I will be talking today in more detail, is the transformation that leveraged the P-complexation of aromatic ring with earth-abundant transition metal. And here, in fact, we're trying to activate the CH bond and also the CC double bond. So just a quick overview of our iron photocatalyzed project. So here I would like to highlight this work on the iron photocatalyzed decarboxylative oxygenation with tempo, which have been developed by my amazing PhD students, Luca, Megna, and Jason, where they develop a very general reaction, which have a very good substrate scope and high functional group tolerance. But even more importantly, in collaboration with other groups here at Bonn, such as the group of Patricia Kiel, Olaf Schirmann, and Barbara Kirchner, we have been able to develop to study the mechanism of this transformation in much detail, and we found some very nice aspects of this mechanism. So I really invite you, if you're interested in this type of chemistry, to have a look at our work that had been published last year. So now, today, in fact, I would like to talk about the selective CH correlation of polyaromatic compounds. And in fact, the selectivity in this project is enabled by the metal complexation, P-complexation to the arene. So this work has been done by very talented postdoc, Anoop, and PhD students, Clemens, Kavin, and Ruben. And before to talking about the project itself, I would just like to make a quick overview of some aspects, general aspects of transition metal catalyzed CH functionalization. So if you look at this molecule here, and I would ask you to find a method to functionalize, to make derivative of this molecule. And if you have some experience in organic synthesis, of course, the first thing one will try to identify this functional group, such as the chloride, and which can undergo a series of cross-coupling reaction. One moment. Oh. And but then, if you have a closer look at this molecule, you can identify a series of CH bonds, and of course, this CH bond can enable much more diversity and than the simple functional group. And of course, it can also increase the step economy of chemical process. But as any type of transformation, of course, the CH functionalization have its challenges, and that is the selectivity. Broadly speaking, the CH functionalization can be divided in two categories: undirected CH functionalization, and of course that will be a very nice approach because it's step economical and one can have a broad applicability. But of course there is drawbacks, and that is the transformation, the breakage of the CH bonds is thermodynamically and kinetically challenging, and in many cases one can achieve not good selectivity. In order to to overcome this selectivity issue, scientists develop tools called directing group, and this directing group coordinate with the metals, and that clearly provide an kinetical advantage, good selectivity, and it's well developed. But unfortunately, because one have to install this directing group and further later remove it, that limit its applicability. So to sum up, for a CH functionalization reaction to be useful, it should activate a single CH bond without reaction at other accessible CH bond or reactive functional group. A particular interesting transformation is the CH functionalization with the boron derivative because it offers unique selectivity paradigm. So here we have a substrate with an electron donating group. And of course, if you would like to activate an ortho position, the method of choice would be ortholithiation, followed by the reaction with electrophile. If you think about the electrophilic aromatic substitution, one can introduce a group in para position if this electron donating group will be big enough. However, the transition metal catalyzed borylation enable unique selectivity because we'll introduce this boron group in the meta position, which will be will offer the more stable metal aryl complex, but more importantly, this transformation is very sensitive to the steric of the substrate. Because of that, in fact, those type of one free substitute iron is the substrate of choice for this type of iridium catalyzed CH borylation. But now the question I would like to ask is that you ask yourself: can this strategy be applied for the selective CH borylation of polyaromatic compounds? You can think about it. I will just make a quick introduction on why someone will be interested on accessing borylated polyaromatic compounds. The motivation is pretty simple, in fact, because you can find polyaryls in many drugs, agrochemicals, and OLED materials, and so on. And if you look what is the best way of accessing these polyaromatic compounds, the method of choice is the Suzuki-Miura cross-coupling, where you take one aryl boronic acid derivative and you couple with electrophile. But now the question is, how can one efficiently access the polyaromatic organoboron compounds? And of course, if we can directly access this molecule by direct CH borylation, that will be of much interest. But now let's come back to the question, can we really apply directly this CH borylation to polyaromatic compounds? And as I mentioned before, if you have just simple aromatic ring with one substituent, you'll have a selectivity issue in terms of ortho, meta, and para position. And now with many development in terms of ligands, we can to some extent control which position will be activated. But then if you introduce a second aromatic ring, the situation becomes a little bit more complicated. And of course, if you introduce a third aromatic ring, you will get an untraceable reaction mixture. So in fact, that is the challenges associated with direct CH borylation of polyaromatic compound. That is really the low selectivity. So let's have a look how people try to directly borylate the polyaromatic compounds. And here you have an example which uses classical iridium catalyzed CH borylation with terz-butyl bipyridine ligand. But if you pay closer attention to this substrate, you can clearly see that this ring is sterically biased, and as well this one. Another approach is this directed CH borylation, but as you can imagine, the requirement, the presence of this directing group limit the applicability of this strategy. Another approach was this cooperative catalysis between iridium and aluminum, where one can selectively borylate the pyridine-containing aromatic ring in this para position. And finally, a very nice report by Chirik, which is a cobalt catalyzed selective CH borylation and of fluorinated aromatic molecule. And here, in fact, they observe a very good selectivity for the borylation in ortho position to the fluorine atom, which make the most strong, the most stable cobalt aryl bond. But as you can see, what all these precedents have in common is really that the substrate in all the cases are somehow biased. So what we try to do is to do the borylation of polyaromatic compounds where we don't have a necessarily structural bias of the polyaromatic component. So for that, we use this chromium tricarbonyl unit in order to electronically enhance, differentiate the aromatic rings, which is complex versus the one that is not complex. So what is the logic behind this idea? In fact, what is known is that once the chromium tricarbonyl unit complex the aromatic ring, that reduce drastically the electronic density on this aromatic ring and increase the pKa of the CH bond. And in fact, this strategy was previously applied by the La Rosa group to activate for the palladium catalyzed CH arylation of anisole and aryl fluoride, this quite selective one in ortho position. So in order to test our hypothesis, if really this chromium tricarbonyl unit can enhance the reactivity of the CH bond towards the CH borylation, we conducted the following experiment. So we take one equivalent of this aromatic ring, which is complex with chromium tricarbonyl unit here. And then we use a large excess of simple 1,2-dimethoxybenzene. And we conducted this reaction with short reaction time at room temperature. And in fact, we found that there is a strong difference in the reactivity of these two substrates. So in fact, the chromium complexed aromatic ring react 100 times faster than uncomplexed one. So clearly that can provide us enough of the differentiation for the selective CH borylation of polyaromatic compounds. So in order to further assess the effect of this chromium unit on the CH, on the reactivity of aromatic ring in the context of the CH borylation, we took a series of very electron-rich substrates which are known to be particularly challenging for the for iridium catalyzed CH borylation. And we conducted this reaction with one equivalent of starting compound at 30 degrees. And in this situation, we observe very low yield or no reaction. So then when we increase the reaction temperature to 80 degrees, we could observe relatively good yields for a certain substrate, but still quite poor with other. However, when we do the same reaction with the same substrate that are coordinated with chromium tricarbonyl unit at 30 degrees, we can see a clear advantage of that because the yields are very high or even quantitative. So now let's move to more interesting substrate scope of this reaction, and that is really the polyaromatic system. So at the beginning, we took this symmetrical bisaryl to start with more simple system, and we applied the developed condition. And in fact, we found that the CH borylation is taking place in high yield and very good selectivity, almost exclusively on the aromatic ring that is coordinated with chromium tricarbonyl unit. So then we did the same with substrate that have two different aromatic rings. And again, we observe very good selectivity and good yield. Then we introduce also the heteroaryls, and in both cases, we see very good yield and exclusive selectivity. Same can be said in the case of the polyaromatic compound containing 3 aromatic ring and 4 aromatic ring. So then we extended this to 5 aromatic rings, and here you have another very nice example with 4 aromatic rings. And in the end, we have this very nice substrate, which have one phenol-substituted moiety and this bisphenyl. In all cases, we see very good selectivity and very good yield of monoborylation. So of course, the question that I'm sure many of you asked, how really do you get this the substrate, like the starting material, how you selectively introduce this chromium triscarbonyl unit on this polyaromatic system. So in fact, how we doing this, we taking this boronic acid derivative and we cross couple with aryl chloride that is coordinated with chromium. And in fact, we get very good yield for this transformation, and reaction is taking place under very mild condition with aryl chloride. When we try to do the same reaction with uncomplex aryl chloride, in fact, we get very poor yield, and we have to switch to the aryl bromide in order to achieve good yield for this cross-coupling reaction. And that clearly indicates that besides being a very useful group for the selective CH correlation, it also enhances the activity of the aromatic ring towards the cross-coupling reaction. So now when we subjected this chromium polyaromatic compound to the borylation, and then we directly shine light on this reaction mixture to remove the chromium tricarbonyl unit, we can obtain a single regioisomer. So we obtain only one compound via this sequence. However, when we try to do the same reaction, iridium catalyzed CH borylation of this uncomplexed polyaromatic system with B2Pin2, we see a very complex mixture which generate more than 10 products, where we have the mixture of mono, bis, and tris borylation product. And that clearly highlights that our strategy of the complexing and electronically differentiating this aromatic ring in the context of, in the presence of other aromatic rings is very powerful strategy to selectively borylate the polyaromatic compounds. So then just a quick overview on the reason why do we see this selectivity. So we did a collaboration with Professor Grimm and his student Christoph Plett on the DFT study of this project. And for that, we applied the reaction mechanism reported by Hartwig on the CH borylation, where this tris boryl iridium complex is responsible to break the carbon-hydrogen bond to generate this iridium-5 complex that after the reductive elimination will provide the product and iridium-free bis-boryl hydride. And in fact, when we conduct this the computation with benzene, so it's not complex with the chromium tricarbonyl unit, we found that this activation energy is around 20 kilocal per mole, and that corresponds to previously reported computational data. And then when we do the same reaction with benzene that is complex with chromium tricarbonyl unit, we can see some two major differences. The first one, of course, is that this activation energy is much lower than in the case of benzene. And secondly, that we observe a much stable iridium-5 complex. So to cut the story short, we found that in fact the rate limiting step in the case of our system is the CH activation, and because we have a lower activation barrier for this this step, that make our substrate, which is complex with chromium, much reactive and much faster. So I will skip, due to the time reason, the reductive elimination of study. And of course, I will come to the last slide of and maybe the most important slide, I will say, of this presentation, where I would like to acknowledge, of course, my hard working group, all the co-workers from Kekule Institute, and of course, our collaborators and the funding agency. Okay, so thank you very much, and I hope I didn't talk too long.
No, that was really nice. Thanks, Ala. Okay, so we start to have questions. Okay, so one question asks if this is CH activation or CH functionalization. So you said it is CH activation.
Yes.
Okay, then Francisco Julia from Murcia asks us whether you can play around with the ligand and chromium to redirect site selectivity in the CH borylation reaction.
In fact, that's a very good question. And yes, we thinking about that a lot. But one have to take in consideration that there is certain property of this ligand that have to be respected to have the same reactivity. So we have to have a very poor, electron poor, like a p acceptor ligand as carbon monoxide to still be able to see such an increase in the reactivity. But yes, it's not easy, but that is our final goal, is really to put a ligand there and maybe to play with the selectivity around. Very good question.
Okay, then there is another question from Joshua Barham again. That is asking if it says that it would be very powerful for late stage functionalization purposes if you could introduce the chromium complex or some other metal complexes exogenously to bind a certain aromatic ring and then direct the correlation there. Is this where you want to go in the future?
So if I understand the question correctly, it's not to introduce the chromium tricarbonyl unit with the aromatic ring via cross-coupling, but to directly
I guess,
introduce.
yes.
Is that correct?
I think so.
Okay, so that would be nice, but in fact, it's not very easy to selectively introduce the chromium tricarbonyl unit when you have a polyaromatic system, one. And secondly, in fact, that is not so important in the case of the polyaromatic system, because generally, okay, if you have a bisaryl, this one you can buy. But if you have more specific polyaromatic system, you have to build this one via cross-coupling. So in fact, the only difference that we'll have this chromium tricarbonyl on the aryl chloride, and then which will play double role. In fact, it can enable a better and a faster CC coupling, but then later on also will enable the selective CH correlation. But yes, one thing that we look forward is how to recycle this chromium tricarbonyl unit. That is kind of the big problem that we want to solve to make this transformation even more useful.
And
practical.
Kind of question for me. You talk about this recycling of the chromium. Of course, there's a lot of eta-6 complexes like manganese and ruthenium, rhenium. Can you use these other metals as well, or chromium is just the right one for correlation?
In fact, we didn't try other metal. Maybe we tried manganese, but chromium is, in our case, worked the best. Like with the manganese, we didn't try so much, but really the chromium is, the advantage is that it's quite stable and it's very easy to synthesize and to purify. So that was a very good starting point. But yes, why not to look later on at other metals?
Great. Okay. Well, thanks again, Anna. That was a really nice talk, and there's a lot of nice messages in the chat about. Wait, there is another. Joshua is actually correcting his point and is saying, I was thinking more towards complex molecules with maybe just one or two aromatic rings rather than polyarenes. Maybe something to think about for the future. I think he's thinking about late-stage functionalizations of drugs and bioactive molecules.
Yes. Okay, yes.
Which would be really, really great, right?
Yes, indeed, that would be nice things to achieve in the future. Yes.
Yeah. Okay. Cool. All right. Thanks, Ala. Good luck for the future for your research plans.
Thank you very much.
Okay. So we have arrived to the end of our webinar today. I just want to thank again Thieme and Synthesis for organizing it. Of course, I want to thank all our 4 speakers for their time and for sharing their exciting results for us. And thank you to everyone for joining this webinar today. Thank you very much.